There are places on this planet that exist beyond ordinary reach. Not because they are distant, but because they are hidden beneath layers we seldom consider. When you look at the ocean, you see a boundary. Water meeting sky. A place where things end. But beneath that surface lies a geography as complex as any mountain range. Valleys deeper than peaks are tall. Walls steeper than anything you could climb. The Philippine Trench is one of these places. It sits southeast of the Philippines. A wound in the seafloor stretching across hundreds of kilometers. At its deepest, it reaches beyond 10,000 meters. To understand that depth, imagine standing at sea level. Now imagine descending the height of Mount Everest. Then descending that same distance again. You still have not reached the bottom. The pressure at these depths exceeds 1,000 atmospheres. The temperature hovers near freezing without changing. Sunlight has never existed here. Not filtered or faded. Simply absent. And yet life persists. Not clinging desperately to existence, but adapted so completely that these conditions feel ordinary. The creatures here know nothing else. For them, crushing pressure is normal. Absolute darkness is home. This is not a story about extremes for the sake of drama. It is a story about how life finds solutions. How adaptation carves possibility from impossibility. How the ocean holds worlds we are only beginning to understand. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries about the natural world, consider subscribing. We create these videos to help you learn and relax at the same time. Let the journey continue. The ocean is not one place. It is many places stacked vertically. Each layer holds different rules, different pressures, different possibilities. Near the surface, light defines everything. Warmth spreads through the upper 100 meters. Plants grow here using photosynthesis. Fish swim in schools that shift like moving clouds. Everything moves quickly. Energy flows abundantly. But step downward and things begin to change. Colors fade first. Reds disappear within the first few meters. Oranges and yellows follow soon after. Blue penetrates deepest, but eventually surrenders. By 200 meters, only shadows remain. This region is called the twilight zone. Animals here develop larger eyes to capture what little light exists. Some begin producing their own glow through chemical reactions. Bioluminescence becomes a language in the dimness. Keep descending. Past 600 meters, light ceases entirely. Vision loses its value. Animals rely instead on vibration, chemical trails, and subtle shifts in water flow. The body becomes a collection of sensors tuned to darkness. Temperature drops steadily. The warm surface layer gives way to cold that never fluctuates. 2 to 4 degrees Celsius becomes constant. No seasons exist here. No day or night. Only the steady cold. Pressure increases with mathematical precision. Every 10 meters adds another atmosphere of force. At 1,000 meters, the pressure reaches 100 times what we experience on land. At 5,000 meters, 500 times. The Philippine Trench begins its true descent around 6,000 meters. This marks entry into the Hadal Zone, named not for drama, but for depth beyond the abyssal plains. Here the rules become absolute. Any structure filled with air collapses instantly. Rigid bones fracture under compression. Traditional muscle tissue fails. The trench walls slope steeply downward. Sediment collects in layers over millions of years. Each layer tells a story of what drifted down and settled. Organic particles, mineral fragments, the remains of creatures from worlds above. Following these walls downward means watching life become increasingly sparse. Not because survival is impossible, but because the strategies for living require such specificity. At 8,000 meters, only specialized species remain. Their bodies contain no air pockets. Their skeletons are thin or absent entirely. Their tissues match the density of surrounding water. At 10,000 meters, the trench floor spreads out in soft sediment. The pressure here exceeds 1,100 atmospheres. Every square inch bears more than 16,000 pounds of force. And still, movement continues. Small crustaceans crawl across the sediment. Fish with transparent skin drift above the bottom. Worms burrow through layers of organic material. The architecture of descent is not empty. It is a ladder of adaptation. Each rung requires different solutions. Each depth selects for different possibilities. Understanding the trench means understanding this vertical structure. How each layer connects to those above and below. How energy flows downward in slow motion. How life at the bottom depends entirely on what falls from heights it will never see. There is a fundamental difference between darkness and the absence of light. Darkness implies that light exists elsewhere, that it could return, that it has simply been blocked or removed temporarily. The deep trench knows something different. Not darkness as a condition, but the absence of light as a permanent state. Sunlight carries energy that builds entire ecosystems. It powers photosynthesis in phytoplankton. These microscopic plants form the base of almost all marine food webs. Small animals eat the phytoplankton. Larger animals eat those animals. The chain extends upward through increasing size and complexity. But all of it requires light. In the Philippine Trench, that requirement vanishes. Nothing grows here from sunlight. No plants exist. No photosynthesis occurs. The foundation of life must come from elsewhere. This creates a dependency unique in nature. Everything living in the trench relies on material drifting downward. Marine snow, they call it. Not literal snow, but aggregations of organic particles. Dead plankton, fecal matter, fragments of larger organisms, mucus strands from gellas. All of it clumps together and sinks. The journey downward takes time, days or weeks depending on particle size. Along the way, other organisms consume much of it. Fish in the twilight zone filter particles. Crustaceans in the midwater pick through aggregations. By the time marine snow reaches the trench floor, only a fraction remains. But that fraction matters absolutely. Animals here have metabolisms tuned to scarcity. They grow slowly, reproduce infrequently, live longer than shallow water relatives. A snailfish in the trench may survive for decades. Its slow metabolism conserving every calorie. When food arrives, it feeds. When food disappears, it waits. Waiting is not suffering here. It is strategy. Some creatures enhance their survival through specialized feeding. Sea cucumbers move across the seafloor, ingesting sediment. Their digestive systems extract microscopic organic particles from the mud. What seems like soil becomes sustenance. Amphipods, small crustaceans abundant in the trench, scavenge aggressively. They detect chemical signatures from decaying material. When something substantial falls, a dead fish or squid, amphipods converge rapidly. Their bodies may be small, but their numbers compensate. Occasionally, something larger arrives. A whale dying at the surface eventually sinks. The journey takes days, the body drifting down through every layer. When it reaches the trench floor, it represents years of nutrition. Amphipods arrive first, guided by chemical trails. Fish follow, tearing at soft tissue. Worms colonize the bones. Bacteria consume what remains. A single whale fall can sustain a local community for decades. The bones themselves become habitats. Microbes colonize them, breaking down lipids stored in the skeletal structure. These microbes support other organisms in a cascade that extends the resource far beyond the initial carcass. But whale falls are rare. Most of the time, the trench receives only the thin rain of marine snow. This creates an ecosystem defined by patience. Predators cannot afford to chase prey actively. The energy cost would exceed the gain. Instead, they wait in position. When something passes within range, they strike with minimal movement. Snailfish use suction feeding, opening their mouths rapidly to create negative pressure. Water rushes inward, carrying prey with it. The entire capture takes a fraction of a second. Then the fish returns to stillness. This pattern, brief action surrounded by long stillness, defines life here. Microbes play the most crucial role. They break down organic material at the molecular level, releasing nutrients that larger organisms cannot access otherwise. Some microbes use chemical energy from minerals instead of organic matter. Where the Earth's crust interacts with seawater, reactions occur. Hydrogen sulfide, methane, and other compounds become fuel. These chemosynthetic communities resemble those at hydrothermal vents, but they require no heat. Only the right chemical conditions. The absence of sunlight removes the rhythm of day and night. No circadian cycle structure behavior. No seasonal changes influence reproduction. Time becomes measured differently. In slow accumulation of sediment. In gradual growth of organisms. In geological shifts that unfold across millennia. Animals here have never seen color. Their world contains only texture, vibration, and chemical presence. They navigate through sensation rather than sight. Some retain vestigial eyes, small and non-functional. Evolutionary remnants from ancestors that lived in lighter waters. Others have no eyes at all. The genetic instructions for building them lost over millions of years. What replaces vision is equally sophisticated. Lateral line systems in fish detect minute pressure changes. Chemical receptors identify specific molecules at incredible dilution. Mechanoreceptors sense vibration through water and sediment. These senses paint a different kind of picture. Not visual but spatial. Not colored but dimensional. The absence of light also affects how animals interact. Without visual displays, communication relies on other methods. Chemical signals released into water. Vibrations created through specific movements. Physical contact during encounters. Mating becomes a challenge. Finding another member of your species in darkness and vast space requires strategy. Some species release pheromones that drift with currents. Others use bioluminescence sparingly, brief flashes that signal readiness. The deep trench proves that life does not require light. It requires energy. and energy can arrive in forms other than photons. Here, energy arrives as organic carbon synthesized far above. It arrives in chemical bonds formed by geology. It arrives slowly, but continuously enough to sustain complexity. The creatures living in permanent darkness are not deprived. They are specialized. Their senses, behaviors, and physiologies reflect millions of years of refinement. They live in a world we can barely imagine. But it is their world completely. And it functions with elegant efficiency. Pressure is invisible but omnipresent. At the ocean surface, pressure equals 1 atmosphere. The weight of all the air above us pressing down. We live within this pressure without noticing. Our bodies are built to accommodate it. But water is far denser than air. Every 10 meters of descent adds another atmosphere. The weight accumulates rapidly. At the bottom of the Philippine Trench, pressure exceeds 1,100 atmospheres. To put this in perspective, imagine taking a weight equal to a large elephant, balancing it on your thumbnail. Now imagine that this is not an extraordinary situation, but the constant baseline. Every organism here exists under this force every moment. The pressure does not push from above. It surrounds completely, pressing inward from all directions simultaneously. There is no escape from it, no position that reduces it. For surface life, such pressure would be catastrophic. Air-filled spaces would collapse instantly. Lungs would be crushed. Swim bladders, which many fish use for buoyancy, would implode. Bones would fracture. Cells would rupture. But the creatures of the trench are not surface life. They have evolved solutions that seem counterintuitive until you understand the physics. The key is not resisting pressure. It is accommodating it. Rigid structures fail because they try to maintain internal space against external force. The pressure finds weaknesses and exploits them. Flexible structures succeed because they allow compression without damage. Snailfish, among the deepest living vertebrates, demonstrate this perfectly. Their bodies appear almost gelatinous. Skin translucent enough to see internal organs. Bones reduced to thin cartilaginous structures. No swim bladder. Minimal mineralization. Their skulls are not solid. Instead, they consist of loosely connected plates. This flexibility prevents stress concentration. The pressure simply passes through the structure rather than crushing it. Their muscles are different too. Surface fish have dense muscle tissue for powerful swimming. Snailfish muscles are thin and watery. They provide enough movement for feeding and positioning. But they do not support rapid bursts of speed. Speed is irrelevant here anyway. Prey moves slowly. Predators move slowly. Rapid movement would waste precious energy. The cellular level reveals even more adaptation. Proteins are complex molecules that must maintain specific shapes to function. High pressure tends to disrupt these shapes. Proteins unfold, losing their ability to catalyze reactions or transport materials. Deep-sea organisms counter this with molecules called piezolites. These compounds stabilize proteins under pressure. They are often simple, organic molecules. Trimethylamine oxide is common. It accumulates in tissues at high concentrations. The presence of piezolites allows enzymes to work normally. Without them, metabolism would fail. Cells would die. Cell membranes face similar challenges. Membranes are made of lipid bilayers. Under pressure, these lipids can pack too tightly. the membrane becomes rigid. Transport across it slows or stops. Deep-sea species adjust membrane composition. They incorporate unsaturated fatty acids. These molecules have kinks that prevent tight packing. Even under enormous pressure, the membrane remains fluid. This allows nutrients to enter cells, waste to exit, signals to pass between cells. All the basic functions of life continue because of these small chemical adjustments. Invertebrates show similar adaptations. Amphipods living in the trench have exoskeletons. But unlike shallow water relatives, their shells contain less calcium carbonate, more protein and flexible organic material. This makes them more pliable. The shell bends rather than shatters. It provides protection without rigidity. Some amphipods accumulate aluminum in their exoskeletons. The source is the surrounding water and sediment. Aluminum appears to help protect against dissolution. The high pressure and cold temperature create conditions where shells might otherwise weaken. Jellies and other gelatinous organisms thrive because their bodies are mostly water. There is nothing to compress. The internal water pressure matches external pressure. They drift effortlessly, unburdened by structural concerns. Their simplicity becomes an advantage. Even the smallest organisms adapt. Bacteria living in trench sediments are called piezophils, lovers of pressure. They grow best under conditions that would kill surface bacteria. Their cell walls are reinforced. Their enzymes are pressure stable. Some cannot survive at normal atmospheric pressure. If brought to the surface, they die. The trench has become their only habitat. Pressure also affects behavior. Animals here move with deliberation. Quick movements create stress on tissues. Slow movements distribute force evenly. You see this in how fish glide rather than dart, how amphipods crawl rather than leap, how worms extend segments gradually rather than contracting suddenly. Everything proceeds at a pace that accommodates the weight of water above. Reproduction must account for pressure too. Eggs cannot contain significant air. They are often heavy and sink rather than float. Some species attach eggs to rocks or sediment. Others release them to drift in the water column. Development occurs slowly under pressure. Larvae grow at rates far slower than surface species. But the development is stable. The pressure does not fluctuate. This consistency allows for precise adaptation. Human exploration of the trench requires extraordinary engineering. Submersibles must have spherical pressure hulls, thick titanium or specialized composites. Windows are small and made of materials that can withstand compression. Even with these precautions, descents are risky. Equipment failures can be catastrophic. The pressure allows no margin for error. Yet the organisms living here manage without metal hulls. Their biology is the hull. Every cell, every tissue, every system designed from the beginning to exist under pressure. What seems impossible from our perspective is their baseline. The weight of water shapes every aspect of life in the Philippine Trench. It determines body structure. It influences chemistry. It dictates behavior. It selects for patience over speed, flexibility over strength, accommodation over resistance. And in doing so, it creates a world where life persists against odds that seem insurmountable. But the creatures here do not struggle against those odds. They exist within them naturally. The pressure is not their enemy. It is simply their environment. In most ecosystems, predators rely on speed or strength. A lion sprints after prey. A hawk dives from height. A shark pursues fish with powerful tail strokes. These strategies depend on energy abundance. Calories are available to fuel muscle. Food arrives frequently enough to replenish what is spent. The Philippine Trench operates under different mathematics. Here, energy is the limiting resource. Food arrives unpredictably and in small quantities. Any organism that burns calories unnecessarily will not survive. This creates a paradox. Predators must eat to live, but hunting costs energy. How do you hunt when hunting itself might cost more than you gain? The answer is patience. Predators in the trench do not chase. They wait, sometimes for days, sometimes for weeks, positioned where prey might pass. Snailfish demonstrate this approach clearly. They rest just above the seafloor. Their pale, translucent bodies blend into the darkness. They produce no light, make no sound, create minimal vibration. Their sensory systems remain alert, detecting the faint chemical trail of an amphipod, the subtle pressure wave from a worm, the microscopic disturbance caused by anything moving nearby. When something edible comes within range, the snailfish strikes, not with a burst of swimming, but with suction feeding. The mouth opens rapidly. Water rushes inward, creating negative pressure. Prey is pulled inside before it can react. The entire event lasts a fraction of a second. Then the fish returns to stillness, waiting for the next opportunity. This method conserves energy dramatically. The fish uses minimal muscle activation. It does not pursue prey across distances. It does not fight or struggle. The strategy succeeds because prey also moves slowly. Amphipods crawl along the sediment searching for organic particles. They do not expect sudden attacks. Their defenses focus on detecting chemical warnings or vibrations. When a snailfish remains perfectly still, it becomes nearly undetectable. Other predators use variations of the same principle. Deep-sea eels, elongated and flexible, hide in sediment. Only their heads protrude. They wait for small fish or crustaceans to pass. When something comes close, they lunge with minimal body movement. Grenadiers, also called rattles, move slowly across the trench floor. They use barbels, whisker-like projections to probe sediment. These detect prey buried beneath the surface. When they locate something, they use their mouths to excavate it. The entire process is methodical. No wasted motion. Every movement purposeful. Amphipods themselves act as predators despite being small. They scavenge primarily, but will attack injured or dying animals. Their strategy involves gathering in groups when food appears. Individually weak, collectively effective. When a fish carcass settles on the trench floor, amphipods detect it through chemoreception. They follow the chemical gradient to the source. Dozens or hundreds may converge. They consume tissue efficiently. Their mandibles tear small pieces. They ingest rapidly, knowing the opportunity is temporary. Other scavengers will arrive. Larger predators might displace them. The resource will not last. This creates brief periods of intense feeding, surrounded by long periods of fasting. The ability to survive without food for extended periods is critical. Many trench animals can endure weeks or months between meals. Their metabolism slow to minimal levels. They enter states resembling dormancy. Heart rates decrease. Digestion nearly stops. Movement ceases except for essential functions. This is not starvation in the way surface animals experience it. It is controlled metabolic suppression, a deliberate strategy for energy conservation. When food finally arrives, the animal can increase metabolism, digest the meal, store energy as fat or specialized tissue, then return to low-power mode. Some species have expandable stomachs. They can consume meals larger than seems possible. The stomach stretches to accommodate. This allows them to take full advantage of rare abundance. Bioluminescence adds another dimension to predation in some regions. While uncommon at the trench floor itself, the waters above host organisms that use light strategically. Anglerfish are perhaps the most famous example. A modified spine extends in front of the mouth. At its tip, a bioluminescent lure. The fish positions itself and waits. The lure glows faintly in the darkness. Small fish or crustaceans, curious or mistaking it for food, approach. When they come close enough, the anglerfish opens its mouth rapidly. The same suction feeding mechanism. The prey disappears in an instant. The lure requires energy to produce light, but the energy cost is offset by successful captures. The strategy works because prey in darkness have few visual references. Any light draws attention. Other fish use photophores, light-producing organs along their bodies. These create patterns that may attract prey or confuse predators. A sudden flash can startle a predator long enough for escape, or it can draw curious prey within striking distance. The use of light is always measured, never wasteful. Each flash serves a purpose. Chemical hunting is equally sophisticated. Many predators release attractants into the water. These chemicals mimic food sources or other signals. Prey responding to the signal move closer. The predator remains still until the optimal moment. This method requires understanding the chemical language of the environment. Different species respond to different compounds. Successful predators have evolved to produce the right signals. In all these strategies, patience is paramount. A predator that chases every potential meal will exhaust itself. A predator that waits for high-probability opportunities will survive. The trench selects for restraint, for calculation, for efficiency. Even apex predators here are not aggressive in the way surface predators are. They do not dominate through violence or constant hunting. They dominate through superior energy management. The relationship between predator and prey creates balance. Prey populations remain stable because predation pressure is low. Predators cannot eliminate prey even if they wanted to. The energy cost would be unsustainable. Instead, predation acts as selection pressure. Prey that move carelessly or fail to detect threats are removed. Those with better sensory systems or cautious behavior survive. This drives gradual refinement in both groups. Predators become more patient. Prey become more vigilant. The ecosystem maintains equilibrium through this mutual refinement. The trench demonstrates that predation does not require ferocity. It requires adaptation to available energy. Where energy is abundant, predators can be active hunters. Where energy is scarce, predators become patient ambushers. Both strategies are effective. Both are products of environmental pressure. The patience of trench predators is not passivity. It is active strategy refined over millions of years. Waiting is their hunting. Stillness is their weapon. And in this, they are as successful as any predator in any environment. The Philippine Trench is not a static feature. It is the visible result of forces operating on geological time scales. Beneath the ocean floor, tectonic plates move constantly. Their motion is measured in centimeters per year, imperceptible on human timescales. But over millions of years, this movement reshapes continents and ocean basins. The trench forms at a convergent boundary. Two plates meet here. The denser oceanic plate descends beneath the other. This process is called subduction. The descending plate does not slide smoothly. It grinds downward through immense friction. Rock breaks under stress. Fault lines form and shift. Earthquakes release accumulated tension. These earthquakes are not minor. The Philippine region experiences some of the most powerful seismic events on Earth. Magnitude 8 or greater. Energy releases equivalent to millions of tons of explosives. At the surface, these events cause tsunamis. Underwater, they reshape the trench itself. Sediment layers that accumulated over centuries can shift in seconds. Slopes collapse, sending avalanches of material downward. The trench floor receives sudden influxes of sediment and organic matter. For organisms living here, these events are catastrophic disturbances. Animals buried in sediment die. Habitats are destroyed. Chemical gradients shift suddenly. But life here has evolved with these disturbances as part of the environment. Some species can burrow quickly when they detect vibrations. Others retreat to crevices in rock formations. Microbes respond to changed chemistry by adjusting their metabolism. After the initial disruption, opportunities emerge. Sediment disturbance exposes buried organic material. Nutrients that were locked away become accessible. Scavengers converge on areas where animals died in the collapse. Within weeks, the ecosystem begins recovering. This cycle, catastrophic disruption followed by gradual recovery, defines the geological influence on life. The subduction process also creates chemical opportunities. As the oceanic plate descends, it carries water trapped in minerals. Heat and pressure release this water, along with dissolved compounds. Fluids rich in hydrogen sulfide, methane, and metals rise through cracks. Where these fluids reach the seafloor, they create unique habitats. Microbes colonize these zones using chemicals as energy sources. They perform chemosynthesis instead of photosynthesis, building organic molecules from carbon dioxide using chemical energy. These microbial communities support larger organisms. Worms, clams, and other invertebrates feed on the microbes. Fish feed on the invertebrates. An entire ecosystem can exist around a chemical seep. Videos like this take time to create. If they help you relax or learn, subscribing helps the channel continue. The trench walls themselves are landscapes. Steep slopes descend at angles approaching vertical. Sediment accumulates on flatter sections. Rock outcrops jut from the walls where harder material resists erosion. These variations create microhabitats. Some organisms prefer bare rock for attachment. Others need sediment for burrowing. The distribution of species follows the distribution of substrate types. Geological maps of the trench reveal complexity invisible from above. Ridges run parallel to the main trench axis. Secondary faults branch from the primary subduction zone. Volcanic seamounts rise from the seafloor nearby. Each feature influences water flow and sediment distribution. Currents moving along the trench walls interact with topography. They speed up over ridges, slow down in depressions, create eddies behind obstacles. These flow patterns determine where marine snow accumulates, where oxygen-rich water reaches the bottom, where larvae settle. The geology shapes the biology directly. Even temperature variations, small as they are, link to geology. Most of the trench maintains temperatures near 2 degrees Celsius. But areas with active seepage may be slightly warmer. The heat comes from Earth's interior. It flows upward through fault zones. These warmer pockets host different microbial communities, heat-tolerant species that cannot survive in surrounding cold water. The age of the trench is measured in millions of years. The current configuration began forming in the Miocene epoch, but the processes creating it are much older. Plate tectonics has operated since Earth's crust solidified. This means the trench environment has existed long enough for evolution to produce specialists, species that live nowhere else, adapted so completely to trench conditions that they cannot survive in shallower water. These endemic species represent evolutionary endpoints. Their lineages have been isolated in the trench for long enough to diverge from surface relatives. They are not primitive or simple. They are highly derived specialists. The geological forces continue operating. The Philippine plate subducts beneath the Sunda plate and Eurasian plate in this region. This motion will continue for millions of years. The trench will deepen, widen, shift position slightly. Mountains will rise on the overriding plate as material scrapes off the descending plate. Volcanoes will erupt as melted material rises. The entire region is geologically active. This activity connects the trench to global processes. Subduction zones return oceanic crust to the mantle. This recycling balances the creation of new crust at mid-ocean ridges. Without subduction, Earth's surface would constantly expand. The trench is not just a deep hole. It is a fundamental part of how the planet operates. Understanding life here means understanding geology. The organisms depend on stable conditions, but those conditions exist within a dynamic system. Earthquakes disturb but also renew. Chemical seeps provide energy independent of sunlight. Sediment accumulation creates habitat. Life and geology interact constantly. The slow collapse of one plate beneath another builds the stage. Life performs on that stage with adaptations shaped by its structure. Neither exists independently. As we consider the trench environment, this relationship becomes clear. The biology is impressive, but it cannot be separated from the geology that creates and maintains these extreme conditions. The forces moving tectonic plates are the same forces that make life possible here. By creating depth, they create pressure. By creating earthquakes, they distribute nutrients. By generating chemical gradients, they provide energy. The collapse is slow, measured over millennia, but its effects are present every moment. In the weight of water pressing down, in the sediment accumulating particle by particle, in the rare earthquakes that reshape everything temporarily. The trench is alive with geological processes, and life has learned to exist within them. When you think of an animal, you probably picture something with structure. Bones that hold shape, muscles that attach to those bones, a defined form that persists whether the animal is active or still. This structure works well on land and in shallow water. Gravity and normal pressure require support. But in the Philippine Trench, these assumptions fail. The immense pressure makes rigid structures dangerous. Air spaces are impossible. Dense bones are liabilities. Traditional anatomy becomes a weakness. So life here has found different solutions. The Hadal snailfish, found in several deep trenches including this one, embodies these solutions. Its body appears fragile at first glance, pale, almost translucent, soft to the point of seeming gelatinous. But this softness is precisely what allows it to survive. The skull is not solid bone. It consists of loosely connected cartilage plates. These can compress slightly without breaking. The spine is thin and flexible, more like a supportive rod than a rigid column. Ribs are minimal or absent. They would serve no purpose and add unnecessary weight. Internal organs are surrounded by watery tissue. This tissue has the same density as seawater. Pressure passes through it without causing damage. The fish has no swim bladder. That air-filled organ would implode instantly at this depth. Instead, buoyancy comes from lipid-rich tissues. Fats and oils are less dense than water but incompressible. They provide lift without creating vulnerable spaces. The snailfish's muscles are thin. They generate enough force for slow swimming and positioning. But they cannot produce rapid bursts of speed. This limitation does not matter. Speed offers no advantage here. The skin is loose and elastic. It can stretch as the fish moves through pressure gradients. Thick mucus coats the surface, reducing friction. Even the snailfish's metabolism reflects this structural flexibility. Proteins in its cells contain high concentrations of stabilizing molecules. These prevent proteins from denaturing under pressure. Cell membranes have unusual lipid compositions. They remain fluid despite cold temperatures and compression. The result is an organism that looks fragile, but is perfectly suited to its environment. Other fish show similar adaptations. Grenadiers have elongated bodies with tapered tails. Their bones are thin and poorly mineralized. Large heads contain sensory organs, but little else. Eelpouts, snake-like fish of the deep, are almost entirely muscle and skin. Their skeletons are minimal. These fish are not weak. They are efficient. Removing unnecessary structure conserves energy. It eliminates weak points where pressure could cause failure. It allows flexibility that rigid anatomy would prevent. Invertebrates take this principle even further. Amphipods in the trench have exoskeletons, but theirs differ from shallow water relatives. Less calcium carbonate makes them more flexible. Higher protein content provides strength without rigidity. Some deep-sea amphipods grow surprisingly large. Specimens longer than 10 centimeters have been recovered from trenches. This gigantism may result from several factors. Long lifespans allow gradual growth. Reduced predation pressure eliminates the need to mature quickly. Larger size may help with thermoregulation or nutrient storage. Whatever the cause, these oversized amphipods are well adapted. Their flexible exoskeletons compress under pressure without shattering. Their large bodies house efficient digestive systems. Their sensory antennae detect chemical gradients across great distances. Sea cucumbers represent another approach. These animals are almost entirely soft tissue. No bones. No rigid structures. Their body wall is tough but flexible. Collagen fibers provide some resistance without preventing deformation. Inside, a water vascular system distributes fluid pressure evenly. This acts like a hydraulic skeleton. As external pressure increases, internal pressure matches it automatically. No stress accumulates. No risk of collapse. Sea cucumbers move slowly across the trench floor. Their tube feet extend and retract in coordinated waves. They ingest sediment, extract nutrients, and expel the rest. This process continues steadily, independent of pressure. Jellyfish and comb jellies thrive at depth for the same reason. Their bodies are over 95% water. The remaining structure is thin tissue layers. Pressure compresses them evenly. They maintain their shape through internal water pressure, matching external pressure. Their simple anatomy becomes advantageous. Tentacles drift through the water, capturing small prey. Digestive cavities process food efficiently. Reproductive organs produce eggs or sperm when conditions allow. All of this happens without bones, complex organs, or rigid support. Even worms adapt through softness. Polychaete worms burrow through sediment. Their segmented bodies flex in any direction. Pressure affects all segments equally. Some deep-sea worms grow to surprising lengths. Meters long but only centimeters wide. Their elongated form maximizes surface area for gas exchange and feeding. Their tissues are soft and permeable. Nutrients can diffuse across body walls. Waste products leave the same way. This simplicity works because the environment is stable. No predators specialize in crushing prey. No need for armored defenses. Softness provides all necessary protection. The absence of hard structures affects reproduction too. Eggs cannot have rigid shells. They would crack under pressure. Instead, eggs are soft and flexible. Yolk provides nutrition. Membranes allow gas exchange but resist compression. Some species produce eggs with high lipid content. This makes them slightly buoyant, drifting slowly upward. Others attach eggs to rocks or sediment. The eggs remain in place throughout development. Larval forms, when they exist, are also soft-bodied. They drift in the water column, feeding on microscopic particles. Development proceeds slowly. Months or years may pass before reaching adult form. This extended development requires stability. The environment must remain consistent. The trench provides that consistency. Temperature does not fluctuate. Pressure changes only with depth, not time. Chemistry remains stable, except during rare disturbances. These conditions allow soft-bodied larvae to develop successfully. The prevalence of soft bodies in the trench demonstrates a fundamental principle. Evolution does not move toward complexity for its own sake. It moves toward solutions that work. In shallow water, rigid structures work well. They provide leverage, protection, and stability. In the deep trench, soft structures work better. They accommodate pressure, conserve energy, and eliminate weak points. Natural selection has repeatedly favored softness here. Different lineages, unrelated to each other, evolved similar solutions. Fish reduced their bones. Crustaceans softened their shells. All body types converged on flexibility. This convergent evolution highlights how strongly environment shapes form. The trench demands specific solutions. Life provides those solutions through whatever genetic pathways are available. The result is an ecosystem where traditional anatomy is rare, where softness dominates, where structure comes from tissue pressure rather than skeletal support. It is a world of forms without frames, and those forms function perfectly within their environment. Communication requires transmission. A signal must travel from sender to receiver, crossing the space between them. On land, we use sound and light primarily. Words carry through air. Gestures travel as reflected photons. In shallow oceans, these methods still work. Fish see each other's colors. Whales sing across hundreds of kilometers. But in the Philippine Trench, traditional communication becomes nearly impossible. Light does not exist except what organisms create themselves. And producing light costs energy that is precious. Sound travels well through water, but many deep-sea organisms lack specialized hearing structures. They did not evolve in environments where sound communication mattered. So how do organisms communicate in complete darkness? Chemical signals become the primary language. Water is an excellent medium for chemical transmission. Molecules dissolve and disperse through currents. They persist longer than sounds or light flashes. Organisms release chemicals intentionally or as byproducts. Either way, these chemicals carry information. A dying animal releases specific compounds. Decomposition creates a chemical signature. Scavengers detect this signature from surprising distances. Amphipods, with their sensitive chemoreceptors, can find food sources hundreds of meters away. They follow concentration gradients, swimming toward increasing chemical density. This is not conscious navigation. It is behavioral programming. Receptors detect molecules. Neural pathways trigger movement toward the source. The result is efficient food location without vision or maps. Reproductive communication also relies on chemicals. Many deep-sea species release pheromones. These are specialized compounds that signal reproductive readiness. A female may release pheromones that drift with currents. Males detecting these compounds follow them upstream. The gradient leads them to the female. This method works across large distances. A single female can attract males from throughout her depth range. Timing matters with this strategy. If both sexes release gametes simultaneously, fertilization succeeds. If timing is off, the opportunity is lost. Some species have evolved to release all gametes at once. Eggs and sperm mix in the water column. Fertilization happens externally. This strategy reduces the need for physical contact. Finding another individual in darkness and vast space is difficult. Finding their chemical signature is relatively easier. Tactile communication exists but is limited. Some species use physical contact during mating. Males may grasp female using specialized appendages. This ensures gametes are released in proximity. Other interactions are less intentional. Animals bumping into each other in darkness may simply move apart. No aggressive displays. No territorial disputes. Resources are too scarce for territoriality. Defending space costs energy without clear benefit. Vibration provides another communication channel. Many organisms detect water movement through specialized sensors. Lateral line systems in fish. Mechanoreceptors in invertebrates. When an animal moves, it creates pressure waves. These waves propagate through the water. Other animals detect these waves and can interpret them. The size of the wave indicates the size of the source. The frequency indicates speed of movement. The pattern might identify the species. Predators use this information to locate prey. Prey use it to detect approaching threats. It is communication without intention, but it functions as information transfer nonetheless. Bioluminescence, though rare at the trench floor, still plays roles where it exists. Some organisms use brief flashes as distress signals. When attacked, they flash brightly. This may startle the predator, or it may attract a larger predator to the scene. Either outcome benefits the prey if it can escape during the confusion. Other species use bioluminescence for species recognition. Specific flash patterns might identify individuals of the same species. This helps during mating. It ensures energy is not wasted pursuing incompatible partners. The patterns can be remarkably specific. Number of flashes, duration of each flash, intervals between flashes. All of these can vary to create unique signatures. Some organisms use bioluminescent bacteria. The bacteria live in specialized organs called photophores. The host provides nutrients. The bacteria produce light. This symbiotic relationship benefits both. The bacteria receive food and shelter. The host receives light without producing it directly. This reduces the metabolic cost of bioluminescence. The placement of photophores matters. Some fish have them arranged along their undersides. This creates counterillumination. The light matches faint illumination from far above. Their silhouette becomes invisible to predators below. Others have photophores near their mouths. The light might attract curious prey. Still others have photophores scattered across their bodies. These may serve in species recognition or confusion of predators. Despite these uses, bioluminescence decreases with depth. At the trench floor, almost no organisms produce light. The risks outweigh the benefits. Any light reveals your position. Predators may investigate. Prey may flee. In an environment where stillness and concealment are survival strategies, light is dangerous. So communication at the deepest points relies on chemistry and vibration. These senses operate continuously. An organism constantly samples its chemical environment, constantly monitors for vibrations. Information flows without visual cues or sounds. The absence of traditional communication does not mean isolation. Organisms remain aware of their surroundings. They detect food, mates, and threats. They respond appropriately. The methods are simply different from what we experience. This challenges our assumptions about awareness. We tend to think of consciousness as linked to sensory richness. Sight and sound dominate our perception. But organisms in the trench navigate a complete sensory world. Chemical gradients paint spatial maps. Vibrations indicate presence and movement. Pressure changes signal proximity. Together, these create a coherent picture. The animal knows what is near, what is approaching, what is edible. It knows without seeing. This form of perception is alien to us, but no less valid. The trench environment demands it. Life provides it. Communication continues in darkness. Signals travel through chemistry and pressure. Information transfers reliably. And the ecosystem functions. Organisms find food, avoid predators, locate mates, and rear offspring. All without light. All without sound as we understand it. The signals exist. They simply move through different media. In darkness, other languages emerge, and life remains fluent in them all. There are places on Earth where humans have never looked directly. Peaks in remote mountain ranges, caves extending into unmapped depths, regions of rainforest canopy never climbed. But few environments match the Philippine Trench for sheer inaccessibility. The depth creates immediate barriers. Pressure destroys conventional equipment. Darkness hides everything from view. Cold limits battery life and mechanical function. Even with advanced technology, expeditions reach these depths rarely. When they do, they observe small areas for brief periods. A submersible's lights illuminate perhaps 20 meters. Its cameras capture a narrow field of view. It remains at depth for hours at most. The trench floor stretches across hundreds of kilometers. Most of it has never been seen. What little we know suggests the existence of much we do not. Submersible footage occasionally shows unidentified organisms. A shape moving at the edge of visibility. A trail in sediment from something that passed. Brief glimpses of behavior with no context. Scientists catalog these observations. But without repeated visits or specimens, identification remains guesswork. The organisms might be known species behaving unusually, or entirely unknown species. Sediment cores reveal traces of life that surface sampling never captures. Microbial DNA sequences with no matches in databases. These microbes perform metabolic processes we can only infer. Some use chemical pathways never observed in laboratories. They may process compounds in unique ways, produce unusual byproducts, support food webs we have not documented. Studying them requires bringing samples to the surface. But pressure changes during ascent can kill them. Maintaining pressure during retrieval is possible but complex. Few expeditions have the equipment. The result is that most trench microbes remain unstudied. Geological mysteries persist alongside biological ones. The exact structure of the subducting plate is unclear. How deep it extends, where it melts, what happens to trapped water and minerals. These details influence everything above. If fluids rise through cracks, they create chemosynthetic habitats. If not, those habitats do not exist. Scientists infer these processes from seismic data. But direct observation is nearly impossible. The fault zones beneath the trench are also poorly mapped. Where exactly do earthquakes originate? How does stress accumulate? What triggers sudden releases? Answering these questions requires sensor networks on the trench floor. Deploying and maintaining such networks is expensive and technically challenging. Few exist. Chemical mysteries remain equally profound. Gas hydrates mentioned earlier form in trench sediments. These ice-like structures trap methane. When disturbed, they release the methane. Microbes consume some of it. The rest may dissolve into the water or bubble upward. How much methane exists in these deposits? How often do releases occur? What impact do they have on the ecosystem? Partial answers exist. Complete answers do not. Temperature variations also raise questions. Most of the trench maintains near-freezing temperatures. But localized warming might occur near active faults, or in areas where thermal vents exist. Detecting these variations requires precise measurements. Few have been taken. The movement of currents through the trench is another unknown. Water flows along the walls and floor, but the patterns are complex. Ridges and valleys channel the flow. Sediment affects turbulence. Tidal forces may influence circulation. Understanding these currents would explain nutrient distribution. It would show how larvae disperse. It would reveal connectivity between trench regions. But mapping underwater currents at extreme depth is difficult. Even basic questions about species distribution remain unanswered. Do the same species live throughout the trench? Or do different regions host different communities? Isolation could lead to divergence. Separated populations might evolve into distinct species. But confirming this requires sampling from many locations. Most expeditions visit only a few sites. Reproduction in many species is also poorly understood. When do they mate? How often? What triggers breeding? For species producing larvae, where do larvae settle? Do they drift upward before descending? How long does development take? These questions require long-term observation. Submersibles visit for hours. They cannot watch reproduction events that might happen once a year. Even predator-prey interactions remain incompletely documented. We know predation occurs. We can infer strategies from anatomy. But observing actual hunts is rare. A predator may wait days for an opportunity. Researchers cannot watch continuously. When captures happen, they occur in darkness beyond where lights reach. Or they happen too quickly for cameras to follow. The result is fragmentary understanding. We know the pieces exist. We do not always know how they fit together. Climate change adds another layer of mystery. Surface oceans are warming. Chemistry is changing. Productivity patterns are shifting. Will these changes reach the trench? If so, when and how? The deep ocean responds slowly to surface changes. Decades or centuries might pass before effects become noticeable. But eventually, changes will arrive. Altered temperature might affect metabolic rates. Changed chemistry might influence microbial communities. Reduced marine snow might decrease food availability. Predicting these impacts requires understanding baseline conditions. Those baseline conditions remain incompletely known. Another mystery involves connectivity between trenches. The Philippine Trench is not isolated. Other trenches exist throughout the Pacific. Mariana Trench, Tonga Trench, Kermadec Trench, Japan Trench. Do organisms move between them? Are populations connected? Or has each trench evolved distinct communities? Answering requires genetic analysis from multiple locations. Limited sampling makes this difficult. Technology improves constantly. New materials withstand higher pressures. Better cameras capture clearer images. Improved batteries extend mission duration. Each advance reveals more. But the trench is vast. What we have seen is a tiny fraction of what exists. Every expedition returns with new questions. Unidentified organisms, unexpected behaviors, chemical readings that do not match predictions. These mysteries are not failures. They are invitations. The unknown represents opportunity for discovery. Future researchers will visit with better tools. They will stay longer, sample more thoroughly, see more clearly. Slowly, understanding will deepen, but it will likely never be complete. The trench is too large, too dynamic, too complex. What we learn will always be partial, and perhaps that is appropriate. Some places resist full comprehension. They remain mysterious despite our efforts. The Philippine Trench is one of these places. We can study it, learn from it, marvel at it, but we cannot fully know it. That mystery adds to its significance. It reminds us that Earth still holds secrets. That discovery is ongoing. That wonder remains possible. The journey through the Philippine Trench has taken us through layers of reality most people never consider. We began at the surface where light dominates, where energy flows freely, where life moves quickly and abundantly. Then we descended, through the twilight zone where colors fade, through the darkness where bioluminescence flickers, through increasing pressure that eliminates familiar forms, until we reach the bottom, a place of crushing weight, absolute darkness, near freezing temperature, scarce nutrition. Everything about this environment suggests it should be lifeless. Yet life persists, not struggling, not barely surviving, but adapted so thoroughly that these conditions become ordinary. The organisms here are not remnants. They are specialists. Their soft bodies withstand pressure through flexibility. Their slow metabolisms conserve precious energy. Their sensory systems perceive a world without light. They find food in scarcity. They reproduce without frequent opportunities. They communicate without seeing. Every challenge has been met with solutions. The trench teaches us about adaptation, about how life does not require specific conditions. It requires any stable conditions. Given time, evolution finds ways to thrive. The trench also teaches humility. We have explored less of the deep ocean than the surface of Mars. The vast majority remains unseen. Our knowledge is preliminary, our understanding incomplete. But what we have learned is remarkable. It reveals that life's possibilities exceed our assumptions. That pressure we would consider lethal is merely environmental context. That darkness we would find disorienting is navigable terrain. That scarcity we would call starvation is manageable reality. Life adapts to what exists. The Philippine Trench will continue. Long after this video ends. Long after any human observes it. The amphipods will crawl across sediment searching for particles. The snailfish will wait in darkness for prey. The microbes will process chemicals from the Earth's core. The earthquake activity will reshape slopes. Sediment will accumulate particle by particle. Marine snow will fall like slow rain. The trench does not exist for our observation. It exists because geological forces create it. Life fills it because life fills every available space. We are privileged to have glimpsed this world. Through technology and courage, a few people have descended. They have returned with images and samples, with data and stories. These glimpses inform our understanding. They show us that Earth's diversity extends beyond what is visible. That extreme environments support complete ecosystems. That adaptation knows no absolute limits. The trench remains mostly unknown. But what we do know suggests possibilities we are still learning to imagine. If life succeeds here, where else might it exist? Other trenches, certainly. Other extreme environments on Earth. Perhaps even beyond Earth. The principles revealed in the Philippine Trench apply universally. Life requires energy, stability, and time. Given these, it finds ways forward. As we return toward the surface, the environment gradually becomes familiar again. Pressure decreases. Temperature rises slightly. Light eventually returns. But the memory of the depths remains, of a place where water weighs more than we can comprehend, where darkness is permanent, where life continues quietly. That place reminds us how remarkable life is, not because it conquers adversity, but because it exists within adversity, as though it were not adversity at all. The trench is not hostile to the organisms living there. It is simply their home, and they are perfectly suited to it. If you found this journey meaningful, consider subscribing. We create these documentaries to explore Earth's hidden places, to share wonder, to help understanding deepen. The Philippine Trench is one of many subjects we will explore. Each offers its own lessons, its own mysteries, its own quiet revelations. Thank you for descending into the deep with us, for letting curiosity guide you past comfort into unfamiliarity. The ocean holds more than we can see from the surface. The trench holds more than we can comprehend from above. But by looking carefully, by listening to what science reveals, by remaining open to strangeness, we begin to understand. And in understanding, we find our place, not as conquerors of nature, but as witnesses to its endless creativity. The water covers the trench again. The darkness returns. The pressure remains. Life continues beneath. Quiet, patient, persistent, as it always has, as it always will.